Hi, I'm Marc Hendrix with AIM Geoanalytics in Missoula, Montana, back with the last of our 5-part webinar on the Phosphoria Formation. If you'll recall, our first week, we had a look at the Phosphoria Formation and its equivalents by way of just an overview of the stratigraphy and paleogeography. Week 2, we had a look in a little bit more detail at some of the geochemical evidence within the Phosphoria petroleum system, geochemical evidence for long-distance migration of Phosphoria oils. During weeks 3 and 4, we examined some of the samples of various lithofaces from the Phosphoria in outcrop and in core. And this week, we're going to review the entire webinar and sum up the main points. So this is the summary of our webinar, and it is the 5th and final part in the webinar series. Okay, so just to first remind us all, the Phosphoria Formation is a tremendous, I would say, world-class resource. Not only has it produced a significant amount of the global phosphate that's used primarily as a fertilizer, but here, just as an example, in the year 2018 alone, the Phosphoria produced roughly 2.5% of all global production. These are numbers from the U.S. Geological Survey. In addition to its importance as a source of phosphate, the Phosphoria also really constitutes a major petroleum system itself, including source rock, migration beds, and conventional reservoir. Here, for example, are some other data from the U.S. Geological Survey from 4 basins in Wyoming, showing the percentage of oil that has been produced from these basins that is attributed to a Phosphoria source. And you can see that the percentages are significant, and the total production is also quite significant. So roughly 357 million barrels of oil equivalent and about 1.5 billion BCF of natural gas. Okay, here's a chronostratigraphic chart across the entire Phosphoria Basin from its southern extent in Nevada, Utah, parts of Colorado, across the central Rockies into the northern Rockies here, ultimately into with Montana here. And you can see there are a couple of regional black mud rocks. These are organic rich mud rocks that have provided the source for this Phosphoria oil. These, of course, are the Mead Peak phosphatic shale and the overlying retort phosphatic mud rock. You can see here on this chart that the Phosphoria has both been a source for this petroleum, but it also is currently in some places, for example, the Wind River and the Bighorn Basins, a reservoir for both natural gas and petroleum produced from the Phosphoria. We also see that there is significant production from the underlying Pennsylvania sandstones here in Wyoming, and that is also a reservoir that has mostly Phosphoria sourced oil. Okay, well, this oil is coming from these 2 depositional thicks within the Phosphoria Basin. These are the 2 phosphatic organic rich mudstones, the older of which is called the Mead Peak phosphatic mudstone. These are formal members within the Phosphoria. The younger, of course, is the retort member. And these 2 maps, which we've seen before, show the distribution of these 2 members in terms of their lithofaces, and the organic rich mudstone, of course, is shown in this gray color. And also shown here are thickness isopachs in the pink contour lines, and that's in meters, and then total organic carbon in the green isopleths. And I'll just draw your attention to the fact that the total organic carbon percentages that are recovered from the Mead Peak are typically a little bit lower than the retort. You see here a max of about 8% TOC, whereas in the retort, it can get up to about 30%. But the Mead Peak is considerably thicker than the retort. You have up to 60+ meters of Mead Peak here in southeastern Idaho, and here in the depot center of the retort basin, we're only at about 8 meters total, although again, much more organic rich. All right, so these are the sources of the Phosphoria oil. And just to remind us how we got there, here's a paleogeographic reconstruction from some of Ron Blakey's work. If we're at about 275 million years ago, this is about 5 million years or so before Phosphoria deposition, but it shows the overall paleogeography. A couple of things of note. Here's the equator. the paleo equator, and here's 30 degrees north latitude. So the Phosphoria Basin, which is located right here on the inboard side of this archipelago of islands, and also inboard of a tectonic trench here where this oceanic plate is subducting beneath the North American western margin. This Phosphoria Basin here is located at about 15 degrees latitude north. And that's a latitude and paleogeographic configuration where there's going to be the northeasterly trade winds, which are going to blow across this basin from northeast to southwest. And so one thing I'd want to point out here before I move on to the other diagram on this slide is that the Phosphoria Basin is really isolated from the open Panthalastic Ocean. That is, this archipelago of islands here produces a very circuitous connection by which normal marine water can enter the Phosphoria Basin. And over time, this led to essentially a stagnation of this basin in terms of its water chemistry and preservation of the organic carbon that for which the Phosphoria is famous. Just quickly how that came about, recall we have these northeasterly trade winds blowing across the basin. They're represented by these two symbols here. Here's sea level. That offshore wind or shoreline parallel, it's a little bit oblique, is had the result of blowing surface waters offshore, and those surface waters were replaced by water that was upwelled from roughly a depth of 200 to 400 meters. And that's a significant depth because in this situation, between about 200 and 400 meters water depth, you're drawing water that is actually quite concentrated in dissolved phosphate, which is a critical nutrient that all organisms need to survive. So it's commonly uptaken at the surface to the point where it's gone for the most part normally, but in these upwelling environments, this phosphate-rich water is brought to the surface, and there it drives a very high productivity. So it's kind of a positive feedback loop that is going on here. As the productivity, as these organisms die and sink through the water column, they come to rest in this basin here, and because of the low oxygen that is within this zone of upwelling here between 200 and 400 meters in these depths, the oxygen is used up by aerobic bacteria that are partially decomposing this organic carbon as it sinks to the bottom. Ultimately, the oxygen is used up completely, and you have an anoxic basin here that is developed. And recall then the sill here, this bathymetric sill, is part of this complicated archipelago of islands here that's offshore of the Phosphoria Basin. So we have an oceanic upwelling system that's driving the productivity and a bathymetric configuration that lends itself to anoxia and preservation of this organic carbon. All right, so the overall stratigraphy of the Phosphoria looks something like this. From west to east, we go from the basin, which is where most of the organic carbon is retained today or sequestered in the form of these organic rich mud rocks, the Mead Peak here in dark gray, and the retort, as well as a variety of other cherty members and cherty shale members here in the offshore position. We go then up onto the Wyoming shelf, where those rocks are supplanted by carbonates, and these are oftentimes cherty carbonates. You can see the chert shown here in purple, and then those facies are supplanted even further east by red beds and evaporites. So this is the basic configuration. We're in the main Phosphoria Basin here. The upwelling is basically in this range here, and we're getting up onto the North American craton here as we move up onto the shelf. All right, here's a summary from some of Jim Peterson's work showing what the Phosphoria architecture, that is facies architecture, looks like in western Wyoming in the subsurface. These are derived from three lines of cross-section: A to A prime here in northwestern Wyoming, B to B prime right here in west central Wyoming, and C to C prime here in southwestern and south central Wyoming. In each of these diagrams, what you see are a series of red squiggly lines, and these are denoting sequence boundaries. where relative sea level was at its lowest point. And between those are individual sequences. You can see that these sequence boundaries correlate around western Wyoming and basically subdivide the Phosphoria complex into 3 sequences, one of which is incomplete, and that's the lowermost one here, which only consists of the grandeur member carbonates. The most complete sequence is this middle one here, where you have the lower sequence boundary overlain by Mead Peak. Here it is right here. Here's the Mead Peak and the lower sequence boundary. Here it is right here, this lower sequence boundary. And then that Mead Peak transgressive mudstone is ultimately overlain by high stand carbonates that are part of the Franson and Rex Chert system, and those overlie the Mead Peak, and then ultimately themselves are cut by the sequence boundary that separates this sequence from the third sequence. The third sequence also contains a lowermost mudstone that's transgressive and overlying high stand cherts and carbonates, in this case of the Tosi chert and Hervé carbonate systems. So we do have a very distinct sequence stratigraphic architecture here that has been documented. The one other thing I want to point out before I move to the next slide is that if you notice the distribution of the carbonates, particularly here in CC prime, you'll notice that they're not regional blankets of carbonates. Rather, they seem to be building up over certain regions and more or less absent over other regions. And this is an observation that was made some time ago, suggesting that we actually had Pina contemporaneous vertical tectonics during Permian time that affected the distribution of these facies, and specifically at some of these paleo highs, the Wind River paleo high, the Big Horn paleo high, and those are shown over here in this map that provided for an environment in which the carbonate factory was able to thrive. And in between those paleo highs and the paleo lows, the carbonate factory was essentially shut down, and the lithofacies were dominated more by a mudstone cherty facies. So we have Pina contemporaneous vertical tectonics going on here in Permian time, and that affected the architecture of these rocks, as did relative sea level position. All right. Well, the last thing I want to remind us all about as I draw to a close here in this webinar is this long distance migration of Phosphoria oil out of the depot centers and into the Wyoming basins to the east. Here's a shot from one of the abandoned phosphate mines in southeastern Idaho, showing the Mead Peak and overlying Rex Chert, and you can see that there's quite a big thick section here of phosphatic mudstone that's black in color and organic rich. Here we have an actual sample, a thin section scan from the retort member in southwestern Montana, and this particular sample has a total organic carbon that we measured at AIM to be almost 20%. So this is where the oil is coming from. Just to remind you about the main geochemical evidence behind the correlation between Phosphoria mud rock and Phosphoria sourced oil. Here is the data that was originally published back in 1981 by Seifert and Muldowen. And you can see here on the top panel is a rock extract from a mudstone here from southwestern Montana. And this is a mudstone that was the retort member. And then below it are four mass spectrometer gas chromatic graphs from, that is, distribution of organic compounds from oils produced from Wyoming basins. And so what these peaks represent are individual molecules, individual organic molecules that have a particular configuration and that are known to be derived from organic precursors. And so it's the distribution of these specific organic geochemical compounds between the Phosphoria rock extract and the various produced oils that provide this correlation. In particular, there are these series of blackened peaks that correspond to the biomarker hopanes that are the main correlation markers here between Phosphoria extracts and Phosphoria oils. One last thing I want to point out here is that these are very different from oils in the same Wyoming basins that are generally produced from Cretaceous and younger rocks. And those are correlated with a Cretaceous source. So here we have a rock extract from the Mowry, a Cretaceous mudstone in Wyoming, and below it 4 oils that were produced from Cretaceous and younger reservoirs in Wyoming, in the same Wyoming basins. And you can see here is the distribution of biomarkers is very similar between the Cretaceous source rock and the Cretaceous oils, and the distribution of these biomarkers is quite different between the Mowry source rock and oils and the Phosphoria source rock and oils. So basically we have two petroleum systems here in Wyoming. We have the Phosphoria petroleum system, which has largely charged reservoirs that are older than Cretaceous. And we have the Cretaceous petroleum system that is largely responsible for charging reservoirs that are Cretaceous and younger in these Wyoming basins. Okay, so here's a map showing the former depot center of these Phosphoria source rocks. And so this is basically the Mead Peak Depot Center in southeastern Idaho. And the isopachs here are the restored isopachs between Cretaceous to Permian rock. So what it's showing here is they're quite a bit thicker here in the west, and they thin up onto the Wyoming shelf. But also shown here are the migration pathways of Phosphoria oil from this thermal kitchen, if you will, in southeastern Idaho, where the Mead Peak is thickest, to the east and to the north into the Bighorn basins and the Wind River Basin, and even parts of the Powder River Basin, where Phosphoria oil is actually produced below the Cretaceous. So it is produced from subcretaceous reservoirs. All right, here just kind of to demonstrate that is a couple of cores here that we looked at last week from eastern and northern Wyoming. Specifically, here's the Alvarado Unit 26-2 from the southeastern Bighorn Basin, and this is a Phosphoria core that is locally charged with Phosphoria oil. And then on the right here is the Nance Federal Unit number 7-12, and that's from the Powder River Basin. And it's significant because it consists of the Menalusa Formation, which is older than the Phosphoria. It's Pennsylvanian Permian in age, but it's completely saturated with Phosphoria sourced oil. And again, it's located in the Powder River Basin. So this is just a quick a look at those portions of the overall Phosphoria chronostratigraphic chart, highlighting here in eastern and central Wyoming the fact that we do have Phosphoria sourced oil and natural gas within the Phosphoria itself, as well as below in the underlying 10 Sleep Formation. All right, this slide sums up the facies that we've looked at over the course of these 5 weeks. And again, here's that chronostratigraphic chart for reference. On the left, we see samples that are representative of the organic rich mudstones and phosphorites from the depot centers of the Mead Peak and the Retort in southeastern Idaho and southwestern Wyoming. Here we see a phosphorite that has a lot of diluting quartz. This is from near the base of the Mead Peak, where some of the underlying Pennsylvanian sandstones have been reworked and are forming, are providing the source for these quartz grains, in addition to what you see here, these brown grains, the phosphatic grains themselves. Here in the Wind River Basin, the Phosphoria and its equivalents are largely carbonate in terms of composition, and they're dominated by a brachiopod bryozoan assemblage that locally forms little patch reefs, particularly over the paleo highs and not so much over the paleo lows, again suggesting there was contemporaneous vertical tectonics going on in the Phosphoria Basin at this time that affected the facies. As we get further to the east, these carbonates, which are limestone, largely in the subsurface in the Wind River Basin and parts of the Bighorn Basin, become dolomitized. And so here we see parts of the Alvarado core we saw last week, which include local staining by Phosphoria sourced petroleum. And then finally, here in the far eastern part of the Phosphoria system, we see evaporites, and here looking at the Menalusa Formation, Phosphoria sourced oil that's saturating this Pennsylvanian Permian evaporite bearing sandstone. All right, well, that brings me to our summary here. In conclusion, we have 3 main summaries. Number 1, the Phosphoria is a world-class resource in terms of phosphate, certainly in terms of petroleum, and it is its own petroleum system, source, reservoir, and in some parts of the system, carrier beds. And this was responsible for, this Phosphoria source was responsible for long distance migration of a lot of oils in Wyoming. Number two, we have really three or two with a third part of a stratigraphic sequence consisting of organic rich transgressive mudstones overlain by high stand cherts and carbonates. And our third and final conclusion is that most subcretaceous oils in Wyoming have a Phosphoria source. And it's possible, and in fact likely, that the tar sands in southeastern Utah also may have been sourced by a similar Permian organic rich mudstone, this one from the Eau Claire Basin in northeastern Utah. All right, well, that's it for the webinar. Again, I'm Marc Hendrix from AM Geoanalytics. Thanks for joining us.